You are welcome to the Physics Hub as we continue our journey looking into circular motion. And in today's class, we're looking at how to solve problems involving angular displacement and angular speed. So by the end of today's class, you are expected to solve all the problems involved in angular speed and angular displacement only for a uniform circular path. A uniform circular path. We have been concentrating on the horizontal circle and are continuing to do so. The next part, that's when we look into a vertical circle. Right. So let's quickly look into the concept of angular displacement and angular velocity. What is angular displacement? Now you will see that as the object is moving from point A to point B, there are two displacements taking place. It's moving along the circular path through a distance s. At the same time, the angle between the starting point and the position of the object is increasing. After some time, it will come to a point which we are going to call C. The angle would have changed. After some time, it will go to D. The angle would have changed. So the distance along the circular path is changing. At the same time, the angle between the object starting position and current position is changing. Now, what is angular displacement? Angular displacement, we're looking at the angle through which an object moves on a circular path. From its starting position to the current position, how big is the angle it has gone through? That is angular displacement. You should know that it is measured in radians, and the symbol for a radian is RAD. Now, at A2, if you are an A2 student for CIE, you should be able to define a radian. So a radian is the angle subtended at the center when the arc length S is equal to the radius of the circle. When the distance moved along the arc is equivalent to the radius of the circle, then we say an object has displaced through a radian. This is a very important concept for A2 students under CIE examinations. You should define a radian. So what is angular speed then? Now, since the object is moving and the angle is increasing with time, the rate at which the angle is increasing is what we call angular speed. Angular speed is the rate of change of the angle displaced at the center, and it has a symbol omega. Now we want to use this to solve problems in circular motion. Remember, today's business, we want to solve problems based on angular displacement and angular speed. Therefore, how do we use angular speed and angular displacement to solve problems? Now, from the definition of angular speed, you should come to know that angular displacement is calculated as arc length divided by radius. This equation is key for A2 students doing CIE exams. The angular displacement is the distance along the circumference divided by the radius. So it will come to agree when we're saying 1 radian, S over R, S and R are equal. For instance, we say it's 2 centimeters. R will also be 2 centimeters, giving us 1. So 1 radian is when the distance along the circumference is equivalent to the radius. And this confirms this equation. This equation, you should master it. It's a very important equation. Now, angular speed, we said, is the rate of change of angular displacement. And our angular displacement is S over R. So we can safely say rate means with respect to time. So angular speed is angular displacement per unit time. But this equation can transform and take this shape. The question is how. Let's try to derive the other equation. We know that when an object has gone through the circumference, it has gone through a distance 2 pi r. This is now our s. After going through a circumference, it has gone through a distance 2 pi r, which is equivalent to our s. And we know that the angular displacement theta is s over r, from where this relationship, let me call it relationship 1. Now our s is the same as 2 pi r. So we can safely say theta therefore is 2 pi r divided by this r here, because 2 pi r is for s. The circumference is 2 pi r, which is the distance along the circumference. And we divide it by r, the one from this equation. R will go with r, and we remain with theta is 2 pi. So we can safely say omega is 2 pi over period, when the time to complete the circle is period. Why is it so? It's uniform circular motion. The speed along the circumference remains the same. So the period remains the same. The time to complete a circle remains the same. Now this period is the one which comes here. So we can safely say omega is 2 pi divided by period. Now let's try to relate before we solve any problem. Is there any relationship between tangential speed and angular speed? You will find that there is an equation you need which relates tangential speed to angular speed. And the relationship between speed along the circumference and the angular speed is defined by this equation, a very important equation at A2. Tangential speed is equal to omega r. Tangential speed is equal to omega r. Now, in the last lesson, we agreed that centripetal acceleration is equal to v squared over r. So, based on this relationship, can we find centripetal acceleration using omega? Then we can say yes. Since we know that v is omega r, we can put omega r where there is a v here, in such a way that we say centripetal acceleration is equals to, instead of writing v, we are going to write omega r. Why? V is equal to omega r. Then we square using this square which is here, divided by r. What are we going to get? We'll get our centripetal acceleration is omega squared r times r. This will go with this, and the omega is distributed inside. So this equation is key. Centripetal acceleration is equal to omega squared r. How did we come to this point? We said a c is equal to v squared over r, but v is equal to omega r. So where there is v, we put omega r, which is omega r squared divided by r. What are we going to get? We're going to get omega squared r squared divided by r. One r goes with this one. We remain with omega squared r. This equation is key when solving problems using angular speed and angular displacement. Therefore, we can safely conclude that the centripetal force is m omega squared r squared from Newton's second law. If centripetal acceleration is omega squared r, like here, Newton said F is equals to ma. So we put m times, and we say our a is omega squared r, so we put omega squared r here. M times omega squared times r, it's m omega squared r. So it's very apparent from this position that we can calculate centripetal acceleration using angular speed. We can calculate centripetal force using angular speed. Let's quickly dive into that using an example. A small ball with a mass of 0.2 kilograms is attached to a string and swung in a horizontal circle. If the ball string is 1.5 meters along the ball's, sorry, I'll repeat this. A small ball with a mass of 0.2 is attached to a string and swung in a horizontal circle. If the ball's string is 1.5 meters long and the ball completes one full rotation in 1.2 seconds, calculate the angular velocity of the ball. Right, we need to collect our data. The radius is 1.5. The period is 2 seconds. One full rotation is period. Mass is 0.2. We are looking for on A, omega, which is angular velocity, and on B, centripetal force. So let's quickly recall our equation. We said omega is 2 pi over period. Omega is 2 pi over period. Let's do substitution, which is 2 pi divided by the period of rotation, which is 1.2 seconds. And we are going to get 5.24 radians per second. How do we find the tension in the string? We said the tension provides for the centripetal acceleration from the previous class. And today we said m omega squared r is the centripetal force. From where? From Newton's second law. If F net is equals to ma, then centripetal force is equals to m times centripetal acceleration, which we said is omega squared r. That's how we come to this equation. Substituting numbers for letters, we are going to get 8.24 newtons. Right, I'm going to give you this example and take a break. By the time we come back from the break, you should have solved it. Then we check your answers, you mark yourself. See you shortly. You are welcome back. Now it's time for me to present the solution. Then you mark yourself. So a cyclist rides around a circular path with a radius 100 meters. At a constant speed of 10 meters per second, determine the angular velocity of the cyclist. We are presented with the data, radius 100 meters, speed 10 meters per second. We are looking for omega at item A. Now we discussed that V is equal to omega R. But this question requires us to find omega. So we divide both sides by R so that we remain with an expression which says omega is V over R. So let's recall the expression omega is V over R. Substitute V is 10 meters per second, R is 100 meters, and we're going to get 0.1 radians per second as our angular speed. Part B requires us to find the magnitude of the centripetal acceleration. So let's quickly recall the expression for centripetal acceleration, which is omega squared r. Remember, this thing is coming from tangential velocity. We said AC is v squared over r, but v is omega r. So we substitute where there is v, we put omega r, and we'll come to this expression. Let's substitute numbers for letters. Our omega, we found it on part A, which is 0.1 squared, times our radius, which is 100 meters, given in the question. What are we going to get from the calculators? 1.0 meters per square second. That will be the acceleration. I will leave you with this practice question. Enjoy yourself. Chigo, your senior coach, signing out. See you soon.